This online lecture covers beam bending and the stresses created throughout the cross-section of the beam as forces are applied to the top surface of the beam. Often when we look at beams, we think of simply supported beams and loads that are applied along the top surface of the beam. As you can see here in these two diagrams, there are different types of loads that can be applied to the beam. First, a uniform distributed load as shown on top, or on the bottom diagram, a load that's applied at the center of the beam. This configuration is commonly referred to as three-point bending. Beam bending is a theory that allows us to understand stresses that are created by moments applied at different points along the beam. It's commonly used to understand stresses that are created in very rigid structures of the musculoskeletal system, namely bone. This is one of the different types of loading that can be applied to bone. We've talked in the past about axial loading, which could be compressive and tensile, or torsional loading. And now we're applying moments and understanding how the stresses that are created throughout the length of this beam are different in nature from the axial loading or the torsional loading. This is a complex fracture where the fracture of the bone needs to be realigned, and in realigning it, screws need to be set in place along the length of the bone and then aligned. This alignment creates forces along these beam structures, pictured here and here for the upper and lower leg, respectively. And the analysis of these forces and the resulting moment that are generated by these forces help us understand how to best design these external fixtures so that they don't fail. What I'd like to talk about now are the moments and internal forces that are created not external to the beam structure, but rather internal. As we know already when we study equilibrium, any force that's applied to a structure needs to be balanced by reaction forces applied to the structure. I think by now you know that if this force is applied at the center of the beam and there are y-directional forces supported at point C and point A, we can easily solve for the reaction forces that occur in the y direction at point A in C. You also know from work we've done in the past that if an entire body is in equilibrium, in this case the beam, we can take a section of that body and we know that it must also satisfy equilibrium. If we now take a cut section of this beam, where this indicates the line where we're dividing the beam, and we draw a free body diagram, our first rule is that we apply any of the external forces to the free body diagram, and of course that's our reaction force A sub y here. And at any cut plane, we draw an internal shear force that's often denoted as capital letter V in combination with an internal moment. These are the two forces and moments that we study in beam theory, and this entire structure needs to be in equilibrium. What we're going to focus on for the rest of this lecture is the effect of this moment that's generated internal to the beam and how this moment creates stresses within the beam along this surface. If we take a general beam shown here, this is three-point bending, where there's a force applied at the center of the beam and it's supported or counterbalanced by two reaction forces at the edge of the beam. What we draw here is a general description of how an element within the middle of the beam deforms relative to an initially undeformed or straight segment. This is an expanded view shown here, and what we denote in here is this curvature that appears as a result of this applied loading. And when one examines this curvature, one can look at different fibers that appear along the thickness of this beam here. Again, if we look at the undeformed shape, this would look like a rectangle. As we apply moments, this curvature becomes apparent, and we can track the relative length of fibers along the thickness of the beam. We can track fibers both on the top and the bottom of the beam, and there's a particular location along the thickness of the beam where the length of the fiber in the deformed configuration is no different than the length of the fiber in the undeformed configuration. This is the axis of the beam that's referred to as the neutral axis. there is neither tension nor compression at that point in the beam. We often use a nomenclature to describe the curvature that appears in beam bending. Once again, if we start with a reference rectangular beam cross-section, and this rectangular cross-section forms an arc as shown here, this arc can be described by a radius of curvature denoted by rho in this diagram. This has a certain angle that's associated with that arc, and our nomenclature that we use has a dimension, y, that is defined as the distance from the neutral axis, which is shown here as the sector delta x. As y moves above the neutral axis, that's considered a positive y value. As it moves below, that's considered negative y value. If we look at the fibers that occur throughout the cross-section, we can talk about how the relative change in length of each of these reference elements either decreases or increases as a result of the loading. Because we talk about line segments that increase or decrease, we can naturally talk about the strain that appears along the length of this beam segment that is proportional to the distance from the neutral axis. That strain quantity is related to the radius of curvature, and the text provides you with a full derivation of the equation shown here. What's important to note is how this equation translates to the description that we have for the y-coordinate. Namely, if you move up from the neutral axis in the positive y direction, this equation tells us that by substituting a positive y value in here, this indicates that there are compressive strains above the neutral axis. Likewise, in this situation, there are tensile strains below the y-axis with the curvature shown. One of the natural questions is, where does the maximum occur for this deformation? Clearly, the maximum can occur either at the top or the bottom surface of the beam, and this is defined by the neutral axis and the position of either the top or the bottom surface of the beam relative to the neutral axis. It's natural to then extend our discussion of deformation into a discussion about stress. With Hooke's law, as we know, we can substitute directly for the relationship that we have for strain into a relationship for stress. And we can see very clearly that the maximum strain also follows the maximum stress. It's not surprising because Hooke's law tells us that stress is linearly proportional to strain. One of the things that we often want to describe, though, is the position of this neutral axis, because that defines both the magnitude and the type of maximum stress that is created in beam bending. If we now take a cross-section of the beam and study how the stresses appear, I want to remind you that the neutral axis is an axis where there is no extension or compression. Therefore, there is no strain. As we've talked about already in three-point bending, we find that there is compressive strains that appear above the neutral axis and tensile strains that appear below the neutral axis. Therefore, through Hooke's law, we know that there'll be tensile stresses and compressive stresses both below and above the neutral axis. But it's important to note here that these are linearly varying stresses because the strains are linearly varying. If you now integrate these stresses that occur across both the top surface above the neutral axis and below the neutral axis, you find that there is a net force that acts in two opposite directions. The top half of the beam acts to the left, on the bottom half it acts to the right. And together, this looks like something we've explored in the past, which is a couple. Now, you know a couple are two equal and opposite forces separated by a distance that create a moment. Therefore, we can describe the moment that is generated along any cut cross-section and ultimately relate this to the stresses. First, a notation about the moments themselves. One of the ways we can remember moments, and we're recommending to you, is that moments applied in the direction shown in the diagram indicates a positive bending, which forms a smile face for the beam. In comparison, if we now have moments that are applied in the direction shown here, this creates a frown. So, briefly, positive moments create smiles, negative moments create frowns. Hopefully this is a trick that you'll remember again and again in looking at beam bending. If we look at the moments that are created along the surface, we know already by taking a cut section at the beginning of this lecture we could calculate directly what these moments are. There's other ways that we can now calculate this equivalent moment. As I mentioned 2 slides ago, we have axial stresses that are not constant but vary linearly, and that's indicated by these linear functions here. And if we take an incremental element here, we can calculate directly what the moment is at that point by multiplying this incremental force times the distance it acts from the neutral axis. Of course, if we want to calculate the entire moment across the whole surface, we then sum up the moments created by these incremental forces acting both above and below the neutral axis. And this is what we see here represented as an integral. We then substitute this incremental force with an expression that simply describes the stress acting through some incremental area. If you remember, the stress in the beam is linearly proportional to the distance from the neutral axis and the maximum stress. Therefore, we can substitute this equation into the integral equation above, and we have the following relationship, which tells us that the moment is related to the maximum stress divided by the distance from the neutral axis to the surface of the beam multiplied by an integral. This integral is a quantity that's known as the second moment of area. We'll talk about this quantity in another lecture, and this is the quantity that is used to design the beams in cross-section so that they support a wide variety of loads without failing. One final note on the sign convention for this. If you consider the formula by rearranging the terms in the integral representation, again substituting for I, you find that you can define the maximum stress in the beam as a product of the applied moment at that point in the beam, the area moment of inertia, and the distance c from the neutral axis to the surface of the beam. Relatedly, you can also define the stress that acts at any point in the beam, again as a product of the internal moment, the area moment of inertia, and the distance from the neutral axis. Keep in mind that the negative sign is needed so that a positive bending moment will create compression on the top and tension on the bottom. Now that we outlined the theory and provided you with the governing equations for stresses in the beam, it's worth pointing out a couple of highlights from this lecture. First, remember that beams bend in response to loading that can be either distributed or acting at a point on the beam, and that clearly in response to this force, the beam will deform. Remember though that the amount of deformation will vary through the thickness of the beam. For example, there could be compressive deformation on the top of the beam and extensional or tension on the bottom of the beam. There is one point along the beam as you go through the thickness of the beam that's called the neutral axis, and that's the point where there is no tension or compression and strain, and because there's no strain, there's no stress at the neutral axis. This is an important point to consider and is a reference point in calculating stresses throughout the beam. Remember too that the flexural stress that we talk about the most and we derive equations for is maximum along the surface of the beam. Depending on the geometry of the beam, which is calculated through the second moment of area, this maximum stress can either be maximum at the top of the beam or at the bottom surface of the beam, and depending on the shape of the beam, could vary considerably between the top and the bottom. For symmetric beams, the maximum stress is equal and opposite in magnitude along the top and the bottom surface of the beam.